Welcome back. The final keynote this afternoon is by Michael Förtsch. Michael studied mathematics and physics at the University of Erlangen-Nuremberg. In fact, he wanted to become a teacher. Teacher, right? Great. Then he went for a couple of months to the University of Calgary. Switched back then to Max Planck Institute of Science and Light. Got there a PhD in physics. In parallel, he was for a couple of months, no, nearly a couple of months, foreign research at NIST. I didn't know that was good. Then, after that PhD, he switched to Trumpf. Most of you know Trumpf. Those who don't know that, it is something, so it's a very famous company, right? And he worked there as executive assistant to the CTO of Trumpf, interesting person, for several years, for nearly 2 years, 3 years. Okay. And then he became CEO of a company called Q.ant, which I fell in love with because they do photonic computing. And I think he will be a little bit skeptical because the title is quantum technologies, not quantum computing. Okay, Michael. Go ahead.
So I guess the mic is working. Thanks for being here. I must admit it's my pleasure, and it's the first time that I'm here. Until yesterday evening, I did not understand why it's Kreta, but then I realized. So, right. You already spoiled it. Is there quantum or not in it? Let's find out. So before we go on the computing, this is why you are here. By the way, I'm different to most of you because we build these machines. We are not only developing the algorithms, but we really build the chips. So in that sense, you can literally have an inside-out view from the machinery room. Q.ant was founded in 2018. We're a spin-off of Trumpf, so a pretty unique founding story because Peter Leibing is the CTO and owner of Trumpf. He wrote me on a 2-pager, handwritten, Michael, you should found your own company. And this is how the journey began in 2018.
And this letter came with money?
This letter came with money.
Okay, that's good.
Yeah, of course. I mean, you need money to found a company, right? There is no chance to do it differently. When we started Q.ant, we thought we are never doing computing. We were focusing solely on sensors, and the reason for that was simple. In 2018, Google and IBM were basically at the origin of quantum computing. They were pushing and dominating the field, and we were like, okay, if such big players are stepping into the field, what reason besides dying in 5 years is there in order to do quantum computing? And in 2020, we thought maybe there is a chance to contribute. And that's basically the essence of this. Since then, we basically scaled to more than 100 quantities. How we call ourselves for all of you, it's not Q.ant. We just dropped the U to have a brand name. Q.ant stands for quality, anticipation, novelty, and team. So that's why it's Q.ant. Well, we like to patent what we are inventing. That's the reason why we have in the meanwhile 50 patent families, scaling up to more than 200 patents worldwide. And we had 3 world premieres, all of them, 2 of them in sensing, 1 in computing, and we destroyed 7 coffee machines because everyone was drinking too much coffee in this company. What's the idea behind Q.ant? The idea behind Q.ant, and this is, I went back when preparing for this talk, I went back into the year 2018 before the company was founded. The idea since then is to add something valuable to data processing by using light. So all our products follow on a very simple basis the same idea. We have an entrance. This is where current or electricity goes in. Then you convert it into light, And then on a very simple speaking way, whether the light interacts with nature, you have a sensor. And if it interacts among each other, you have a computational task. And then the information is essentially encoded into light. And at the end of each of our products, it's back converted into electricity. The reason why we're not using electricity is manifold and has to be explained on the individual product. What kind of products are we pursuing? Well, as I said, we started in sensing and then came to computing. The first product which we developed was a particle sensor. Okay, now everyone's like, wow, that's a bit boring. What we're using in this, instead of just using light, we are using superposition states to not only discriminate the size of the particles, but due to this enrichment of the data room, we can simultaneously track the size, the speed, the direction, and also the shape of the particles. And this sensor immediately became a research tool for the company ASML. Great, so the first product is, let's move on. Then we thought, okay, what else can you do, right? We have laser expertise, we have electronic expertise, we know how to code software. Then we thought about, okay, let's go into this magnetic field sensing space. And we started to pursue on the atomic gyroscope. I'm not talking about this, you can catch me in a coffee break or something like that, but we started to work on magnetic sensing. Magnetic sensing means the goal is essentially to grasp the biosignal from the human body only by its magnetic features to control machines. And before I'm coming to the photonics, because this is the main part, I want to share one video. And this is a live from this year's SummerSOC. It's the exhibition. What you see on the right is Katarina. She's our leading system architect. And in this rod, there is our sensor. The sensor is of that size, and it's working in an exhibition hall. And what you're going to see is the following. She's opening her hand, and the prosthetics does the same. Just because the sensor reads the magnetic signals of our body. You see traces, this is the alternation of the magnetic field. The sensor actually is 1,000,000 times more sensitive than the Earth's magnetic field. And it's built in a way that it's not blinded by the magnetic field of the Earth. Because usually you could say, okay, if it's 1,000,000 times larger, then the time, the bandwidth gain product of such a sensor should forbid something like that. But this is due to the fact of quantum mechanics. What we in the end do for the physicists in the room, we sense the Siemens transition of diamond. That's it. And it took us 5 years to come to this stage. So this was to show the credibility. Yes, we know what we are doing. And now let's go into photonics computing, or maybe quantum computing. And I always start talks easy, and I don't have too many formulas in my presentations. I hope you appreciate this. I learned the hard way this morning, and I was thrown back into my studies. I typically try to avoid formulas.
I'm a sadist.
So the big question when we started, okay, so you know quantum machines, quantum computers, maybe we should also call them quantum processors, as they're usually carrying out distinct tasks. They can be built using a variety of technologies, right? Superconducting, like the IBM machines, then we already heard something from ions, solid states, atoms, and so on. There are a lot of materials on the Earth that allow to create qubits. So the question is photonic just another ice cube? Is it something unique? Maybe it's the waffle holding everything else. So what's exactly photonics? Because the obvious thing, photons are different, or light is different, right? Light is just propagating, it's not resting. So when we call them, they're traveling qubits, not stationary qubits. And this in itself has as a consequence that you have to rethink everything that's done in the other technologies. How does such a machine work? Now I said there are no formulas. I just put them in during lunch. Wanted to show that there also some formulas. No, just kidding. The essence of a photonics computer is a beam splitter. Now what does a beam splitter do? It splits beams. Easy, right? You have a laser and after it's pointing towards a beam splitter, and after the beam splitter it's divided. Actually, if you want to understand how to control a computer with us, I walk you through the first example. So assume you have laser beam 1 and laser beam 2. We call them X and Y. You split them into 50-50, and then there is a phi. This changes the phase on one of the two. Now as a consequence, on the second beam splitter, you have a variable interference. So you can now decide whether all the light is passing to the upper, to the lower, or something in between. So this is the core element of any photonic device. And by controlling this phase modulator, you allow for basically encoding your information into the light. This can, if you look at it, it can be done and basically be used as to add two numbers and subtract simultaneously. And in the end, what it does basically, if you summarize it at a detector, you build the square over everything. So what you in the end do basically, you do a multiplication. So this is what these machines can do. They can do it very fast and they can do it very good. They can add things and they can multiply things. And they can do it, it's not the speed of light. It's rather that it's basically streaming. You can do it basically without memories in between. That's the key, because the speed of light in comparison to electrons gives you just a factor of 10. It would not explain why you should use light. And this is how you can parallelize. So if you have one of these unitary cells and you put them onto a chip multiple times, you can start heavily parallelizing your computational task. Each of these elements would allow you for basically one operation, adding or subtracting, and in the end you would just basically multiply or accumulate your vector. That's it. That's the whole trick. If things were so easy. There is a second feature. So we understood we can, for instance, if I go one slide back, so this already basically points towards the heart of such a machine. It's a matrix multiplier, so to say. You can encode a matrix, you can send a vector through the matrix. It's basically interacting with the encoded matrix, the vector, and in the end you get an output vector. So it's a vector matrix multiplier at the end. The second point, or the second peculiarity of this is you can add nonlinearities to the material. Basically, well, what does a nonlinearity do? It causes that it's not linear. Now, in the end, you can use it, for instance, to discriminate between good results or bad results. You can unify, for instance, several wavelengths or informations, or you can also split them if you manage to control the nonlinearity on a chip. And for all of you who are...
Right, does that mean that on a photonic quantum computer I can implement nonlinear functions?
Let's go on a photonic computer, you can implement nonlinear functions.
Yeah.
For the quantum,
yeah, because quantum can only implement linear, unitary, and so on.
Exactly. For the quantum computer, the nonlinear section has a different purpose or different use in the algorithm. So, and this is what I basically show you on this. So basically, if you have two elements on a chip and you can arrange them and control them as you want, you can either go on what I call first, this is a Gaussian Bose sampler, which is a special purpose quantum computing device. And what it takes, in the end, takes a matrix multiplier and nonlinearity, and in the end, a single photon detector. So then you essentially can go into the quantum space and already, for instance, calculate graph problems or isomorphism problems or whatever. So these devices are dedicated to the complex classical problems. If you use the same set without nonlinearity, you can have an AI inference device. I mean, a vector times a matrix is AI inference. And if you add the nonlinearity into a different function, you can use it, for instance, for a coherent IC machine. or as you already said, you can implement nonlinear function as well. The circuits would look more or less the same, so whenever there is an S, this is the indication that you have a nonlinear section on your chip. This is a squeezer, how we call this. Then you have an interference device, you have a detector. If you have an AI accelerator, well, you actually, in this case, if this is one would be for training, you would have a nonlinear interaction, a matrix multiplier, a nonlinear matrix multiplier in the end of the detection. And if you have a coherent Ising machine, you use the output of your chip to feed it into the entrance again. Now, coming to your question, the nonlinearity for the quantum is basically the source for the qubits. So the nonlinear section on the chip would realize that you can have 10 dB of squeezing, meaning you have a pulse which is specified number of 10 photons in a pulse, and this n times. Well, you would not use the nonlinearity after you did the linear algebra. Okay, so it's a toolbox. You can build many of them. And the chip, this is a sketch of such a chip, which we, in that configuration, never built, but this was the start in 2019 when we understood, hey, we can add something to computational tasks. On this chip, there is a zone. This is where these ring resonators are, or tons. This is where actually you start the light you want to use. Then you have modulators on the chip. Well, of course, you want to encode something into your matrix, or you want to represent your matrix. And in the end, there's a detection zone, which in our case is not on the chip due to TRL. You're all theoreticians, right?
No.
No. Okay. Now let's assume you want to build a photonics computer, regardless whether quantum or not. Then there is a whole slew of materials. Because light can be guided. Okay, we have light everywhere. What you need essentially, you want to guide light from A to B on a chip, and you want to basically manipulate it. And they're really, it's not like in the semicon industry where they agreed on let's use silicon. The photonics is a bit more the Wild West. Every company has its own recipe. Of course, we also have our own recipe. What we believed in from the very start, and this was actually the starting point for photonics computing, was that we pursued a material which is called thin film lithium niobate. So it's silicon, a buffer layer, and then a very thin film of lithium niobate on top. And this, among all, it's not superior in all categories, but at least it can fulfill all categories. I'll give you one counter example. Let's go to glass. Glass is very good because glass can be highly intransparent. So highly transparent, sorry. Meaning you don't have loss on your light, because whenever you have loss on your light, well, actually data is lost, right? Simple. The problem is try to get an amorphous material to modulate your pulse. It's a nightmare, because what would you do? It's an amorphous material. In our case, it's crystalline. It's pretty simple. You put basically a diode on top and ramp a voltage, and you already cause a phase change. And this is basically when you go deeper and deeper and compare all the materials, you find, and this is it's starting to basically manifest also in the other companies, that lithium niobate is for data processing in the photonic world one of the best material which we currently have. It doesn't mean it's the best material, but we don't have any better. The big problem is it's not semiconductor compatible. So if you go to a fab like TSMC, if you want to go to a very large end, or if you go to a small fab like GlobalFoundries or X-Fab, and you're asking, hey, can you produce me a chip with lithium niobate? They would say, no, it's the wrong material. I don't use your wafer because then I have risks that I ruin my whole production. So that's the big drawback. It was never established as a semiconductor material. And the second thing is, to the point when we started, the only source for this material was China. Okay, bit risky. Let's jump into
Was or is?
Was.
Okay.
Was. In 2023, last year we basically had our first chips. As So what you see here is the ended structuring devices. This is wherever a modulation on the chip takes place. So this is where you can encode one element of your matrix. And you see already that the light can go on and off the chip. We had in the design phase already a 20 by 20 design, so 20 input to output relation, causing a 400 matrix element, including 800 modulators. So this already scales. January this year, we operated a system containing our first photonic chip. As I said, it's a 4 by 4 matrix, and you can also access it anytime online. So this was another requirement I gave to the team. If we have such a machine, I want that people start playing with it. Now, one peculiarity you can already see on the chip or on the matrix encryption, it naturally encodes without any overhead complex numbers because of the because of light. That's it essentially. And we had the first prototypes of the 20 by 20 chip. What I can say, no, we didn't manage to get this copy into a system up to now. We have still to work on the processing steps to realize this chip, but the 4 by 4 can be approached at any time, and I can send you the Jupyter notebooks that you can do this. Why can we do this? Well, 5 years. We did not only focus on this, and this is now because you asked was or is. We thought it really from the material. So what we did is we built our own thin film lithium niobate. First, to be independent of China. Second, the quality which we receive from China is not great, at least on an industrial level. And this year, finally, we managed to basically build 6-inch wafers, fully reproducible thin film lithium niobate, the first source outside of China, in Stuttgart. And then we have a design and layout team. We do the fabrication, and the chips are manufactured also in a, I wouldn't call it pilot line. I know pilot line in the industry sector means you have a pilot line that fabricates your chips, and you copy and paste the line. It's more of a research line, but it has the capability already to drive 1,000 wafer starts a year, which is it's close to the day production of TSMC. So TSMC manages to operate between 1,000 and 3,000 wafer starts a day, and we managed to do it in a year. But hey, we start. We basically run it until a low-level API, so and this already points to something. What you see here at the core is the photonics unit, but the photonics unit is a very stupid device. It needs instructions, so we also need to take care about the control units, the instruction layers, until we have a low-level API where we can interact with it. And the essential point is the chip doesn't look much different from a distant point of view, whether it's a quantum chip or it should become a quantum processing unit, or whether it should be a photonics computer. There is really no difference. The key elements are the same, the chip would look like the same, the material is the same, even the voltages to operate the modulators would be nearly the same. So the question is what to do with it, and as a startup, well, you should better focus on products that you can sell in 5 years rather than in 15 years, because otherwise you have to argue with your investors. I can flip over this. In the meanwhile, you can also basically, we are integrated in this Kubernetes structure. And the vision for this is the first machine, the 4x4. What you saw is what we believe in is that this photonics approach is becoming an add-on. It's not replacing something in the existing HPC or data center infrastructure, but we can do particular tasks like vector matrix multiplications much better than the semiconductor world can do. On the other hand, we would struggle heavily to take jobs from a CPU and from a GPU as well. So this is the point where we position this type of processors to become one additional element into the whole computing architecture. And the reason for this, it's in the last part. It's called applications, or how to get a share of the computing industry. Because just because you can do it quantum or just because you can do it with light doesn't mean that you have a product. You have to add something valuable. And if we come to this industry, it's an absurd industry. There are three key figures. It's performance, it's energy, and it's cost. And you have to meet all of them. Otherwise, it's unlikely that from a research device you're going to get a table in the semiconductor world. And to give you some ideas how far exceeded this industry is, I've just taken the NVIDIA Blackwell B200. So this card can perform 5,000 tera operations per second on an int8 structure. To all of you, so tera is 10 to the 9. It consumes, oh my god, that's the weak spot. It consumes 1.2 kilowatt electrical power, but still leading that the overall energy efficiency is less than, basically it's 0.2 tops per joule. So this is already pretty good. And the other thing is if you go to TSMC and you're asking basically how much is the untested but packaged chip that's used in this device that they're produced at TSMC, the chip untested of NVIDIA costs you $250. And that's also the truth. We also need to take the cost into account because either you have something really, really heavily to demonstrate on a performance level, then you're accepted, or you somehow have to mix the other figures. Because if you just say it's quantum, it's good for research reasons, but not becoming a part of the industry. Now, we all know this, right? And we also know it's not a law. But this is not the message. What I wanted to basically highlight with this slide is when you go back in history of the computing industry, we had multiple machines, and I had the great joy to visit some of you are already told, the IBM museum. And I observed one of the first card sorting machines. It was pressurized with pressure. And the only thing it did, basically, it sorted cards. So it was a mechanical machine. And then there were several instructions on the way, from the tube to the transistor to the integrated circuits, and all of them had one as an actual goal. They drove actually calculation speed. But the key message is encrypted here. So from the 70s till today, what we basically, the Moore's law, depending on how you say it, how you explain it, what you see is we had technology jumps, but even within the semicon, in 2000 there was the end of a single core, just because the frequency on the chip became too high and the chip's too hot. So what they did is they substructured the chips into several CPUs. This then took them to 2010, and then just maybe some of you are in the room who was using the PlayStation 3 because of its excellent gaming quality. No, because of the graphic card. So this was when I was still at science. We bought, I think, 300 PlayStations plus one. Oh, okay. 300 we used to support us in theoretical calculation tasks, and one was lost. It was for the group room. But what we then figured, basically what all of the computational scientists figure out, hey, you should not per se carry out a job on a CPU just because you have a CPU. Let's think it from the problem, not from the tool. Before I repeat this, what also increased since 2000 was the energy consumption. This is something here today, Microsoft is already putting their data center into the sea because it's cooled for free. Okay, maybe not for free, because if everyone does it, we literally boil the ocean. So maybe it's not the solution. Maybe we should think it from the problem's point of view and think about, is what we are doing really the most efficient way? Or in other words, and I like very simple pictures, maybe we should think about if the screw should be put with a hammer into the wall, or let's invent a screwdriver. The message by that is not because we have a tool that's the best solution, we always have to think it from the problem. And this is my very simple, naive picture. We already had these very elaborate functions where you see NP hard and NP sharp and all these substructures of complex problems. I divide the world in basically 3 categories: the quantum problems, the complex problems, and the classical problems. So the classical problems is plus, minus, multiply, and divide, or a simple scheduling. So we have invented the phenomenon architecture as humans, and I think it's working very well here. For the quantum problems, well, you should better basically naturally have access to quantum effects. So the quantum machine, I think, is granted, and you know one or the other figures. Here's one of them. It's the penicillin molecule with 41 atoms, leading to the requirement that you should have 286 logical qubits. So this is just one point that points towards, well, a classical machine would not entirely simulate this molecule. But the question is, what do we do with the complex problems? So as I said, when we started to basically think about, can photonics quantum computer contribute to the complex classical problems, like the traveling salesman problem, which is often stated, but it's just a representative to have a word. And what we figured out is the following graph. In order that these systems can really contribute in terms of that we can have an advantage from the quantumness of the system, we need the specifications of the system are as follows. We need a transmission end-to-end of 80%, or in other words, only 20% of the data should be lost. We need 16 dB of squeezing, which in that machine was never demonstrated on Earth. And we need 64 modes coherently coupled together. Then we are in the region where we can say we are basically, per definition, faster, and the noise in the systems is so small that any classical machine cannot outperform our system. Now, some of you might back memorize that Xanadu published something. What they essentially did is they went very far into this direction, and they were using more than 200 modes. In contrast to the approach we did, actually they used it on the time. They used the time encoding, not a spatial encoding. So in that sense, they were a bit more relaxed on the losses on the system and on the squeezing. But still, if you talk to them in a private moment, they would tell you they sort of stopped this because they also didn't know what to drive this into quantum advantage. It's not physically impossible, but it's technically very challenging to get these system specifications running. And personally, I believe we will get it done. Not tomorrow, not the day after tomorrow, maybe in 10 to 15 years once we professionalize our chip production. But the question is what to do in between. We can go on the North Star, or we can search for alternatives. And this is what we did. This is a paper which is not from us, but actually we thought about, okay, if we strip everything, if we ignore the quantum sugar, if we go to the very fundamental principle of what our chip does, I said it's a vector matrix multiplier. It's not so sexy, it's not a smart algorithm, it does brute force vector matrix multiplication. And then we started, so this is the MCI approach, which means the Mach-Zehnder approach. And in this diagram, it already points to something that basically says, if you use photonics and you know how to use it properly, you cannot significantly become very faster than the semiconductor industry, but you can get much more energy efficient. And the reason for this is that most of the tasks do not, so if you watch a GPU calculating a matrix, it takes one element from the memory, it takes another element from the memory, it does an add, it stores it in the memory, then it does it iteratively, and then it brings everything back. So you hear the word memory oftentimes. Whenever memory is in the part, it's energy consumption. And this is something you can basically circumvent by using light. What we have not done so far is essentially implementing ways to, I would say, respect the nature of light even more. Because if you just copy and paste digital processes in the photonics world, it's a bit stupid. You can get a bit better, but it's always Hase Igel, right? And this is an invitation to all of you. Let's think about how to use photonics in a better way, because photonics, they're naturally bosons. You can use multiple degrees of freedom simultaneously, and by thinking about new architectures, this could be a contribute to these computing architectures that we currently see. Here's the present roadmap which we are on. So the first machine I showed you, it's in terms of key figures, it's horrible. I mean, you saw the figures from NVIDIA, and we managed currently on it's 10-bit, luckily, but it's super slow and heavily energy consuming. But it was the first demonstrator, actually, that a photonic device was able to carry out a vector matrix multiplication. The machine, which should be operating in August, hopefully, is still relying on a matrix size 4x4, but redesigning the electronics helped a lot. And we're already coming into the mega operations range at nanowatt per operations energy. And by scaling this in terms of matrix size, just by this brute force scaling, we anticipate that by the end of next year we can come into the region where we are depending, okay, this is still in 10-bit, so probably if we go on an 8-bit structure, we can sneak into the tera operations per second regime. And the power would also then be more beneficial in that sense. So this is where we are currently standing with photonics. With all the history, we went basically through all the quantum zoo. We tried very hard to establish a quantum machine. We have one machine realized in the laboratories, and then we realized, hey, if we are ready, probably the market is gone, or it's a super tough race. This is why we decided that we focus on the fundamentals. And for the moment, push quantum to the future, and with photonics, rely on photonics computing. This is the marketing slide. So what we're currently focusing on is the streaming architecture, as we see that this directly has beneficials in terms of performance, mainly energy, and it can become cost comparable if we scale it to this, if we are on the same chip demand size as current graphic cards for AI are. Then once adding the nonlinearity bringing the nonlinearity into the game, we can participate in the training of artificial intelligence, also any other nonlinear action. So this is just one idea. And then once we have this, we believe that the production of the chip is at a quality where quantum comes yet again within reach, which is probably in the next 10 years. So with this, I'm at the end, and maybe there are questions.
Go ahead.
So the slide said the main power consumption is not on the chip. So where is it?
The photonic chip, you mean?
Yeah, you showed the matrix with nowadays performance, August performance, and next to the edge performance. And the headline was the power consumption, the main power consumption here. Yeah, the other one, next one.
It's in the control unit. So actually the photonic chip, now let's even include the laser. The laser has 100 milliwatt times with a 30% efficiency, let's say 300 milliwatt. The modulation itself is only done by voltages, so no current, but this is due to lithium niobate, that you only need voltages to change in order to change the encoding of the matrix, and all the energy is used in the controlling board, so controlling the chip. The chip itself is cold, it's not even absorbing anything.
Which means that's fixed regardless of the chip size.
Yeah. Yeah.
That's great.
Yeah. Yes. That's great.
Any further questions?
Yeah,
Let me ask another one, maybe a stupid one. You showed that this picture of a chip that has 20 by 20 sounds right.
Yeah, somewhere.
Yeah.
Okay. Yeah.
Don't perfect. And now in a matrix you say 16 by 16. So why not 20 by 20?
Yeah. So the idea actually is that we need some of the modulators for controlling. Then we need to encode the vector that goes through the matrix, and by that we reduce it back to 16 by 16. So basically we have a 20 by 20 chip, but it's operating a 16 by 16 matrix. As you have some overhead functions plus the encoding of the vector that's basically going through your... The fun part is that the modulators can be operated in the gigahertz regime. So the fastest one which we built are 18 gigahertz. In this year, in the first generation, it was the clock frequency was 1 megahertz. In the next generation, it's around 250. And individual modulators are already approaching up to 10 and above gigahertz modulation speeds.
What would it take to multiply a million by million matrix with the corresponding vector? No, I'm serious. Could you do that?
We need support.
Not now, but
in principle, yes, but this is something where I would heavily invite theoreticians, because I'm not believing. So what you see here is we scaled the spatial dimension, right? This is coming to an end because you cannot have chip sizes that are larger than the stepper field of your production unit.
And you can't go to a third dimension?
Oh.
No? I have no clue.
No, because the problem with the third dimension is that you have also to consider all the wiring and everything, and it's not invented. So basically the tools are not available. Even the semiconductor industry avoided going into the third dimension for decades because it's not just 1 degree of freedom, it's multi-dimensional complex. But I want to basically shift again the point of view. Why only thinking spatial? You can use wavelengths encoding, temporal encoding, spatial encoding for the information, and for the data processing it doesn't matter. You can also basically have multiple information encoded in close or nearby wavelengths, or you can temporal. So basically light has a huge degree of freedom space that could be applied to encode a million by million matrix. This is where we're currently working on. So maybe next year we can present a different type of architecture. We have some ideas in mind how we can implement this, but everyone is invited to basically participate in this. It's a bit like Parity QC. They also thought the architecture from a different point of view, and I understood today partially how you did it.
Was that correct? No.
No, it was just... sorry.
There's no further question. You want to do a break or?
No. Next
Okay.
session, perfectly fine.
So Michael, thank you very much.